La charla de hoy es Explosive Volcanism and Experimental Earth Science. Realmente es un honor tener a una persona tan calificada y tan ilustre como el profesor Dingwell. Don, it's a honor to have you here, such an illustrious scientist, and we are very thankful to have you here for not only the course, but also for this seminar. Please.
Thank you very much. I don't need
yes, you have.
So good day, everybody, and thank you for coming. And I apologize for the long introduction on behalf of Hugo, if I knew before. So I hope you appreciate that despite the long introduction, I'm a fairly unconventional guy. And I come from a very simple place in Canada and learned everything I knew about sophistication after arriving in Europe, for better or for worse. But of course, as a physical scientist, you have to survive in Europe because we're very direct people. So I always try to give this kind of talk a provocative title to make people's energy a little bit up. And of course, coming to a place like Mexico City and to UNAM, where you all know much more about volcanoes than I do, the whole idea is to challenge you to tell me that you know more. So what I will try to do, and what will be clear, I think, after 45 minutes, is how we work, why we do what we do, and I hope also one or two examples of what it's good for. We're not too worried about what it's good for because we think we're making fundamental advances anyway, and they will eventually be good for something. I know I'm living in Munich in the great university in a highly endowed research system in Germany, living in the island of happiness, as some people say, but it's not so far from one place to the other, and ideas are born from doing unconventional things. So here we go. Explosive volcanism, should it be an experimental earth science? What would we gain? Might we lose something? Am I being too simplistic? Here's a very simplistic diagram. It's probably the simplest description of an eruption that you will ever see in your life. I could have used a point, I suppose, but I used a line. And this is the way that I argued for a big research grant recently, which was to say eruptions are fascinating themselves. That's why we all are interested in studying them, or many of us. But they also are a special thing in the Earth system. They are the way that the lithosphere talks to the biosphere, the hydrosphere, and the atmosphere. They are the conversation on a short-term scale, but with potentially global impact each time that these communications take place. So we should not be surprised that a bioscientist or that an ocean scientist or an atmospheric scientist could be, from time to time, interested in volcanic eruptions. Of course, you all know this, and I will spend no time on it except to say it's everybody's problem. I have to put this up in Munich all the time, because when I came to the University of Munich in 2000, the president was about to give me my certificate for employment as professor. It's a big moment. And when you are officially employed in Germany when your hand touches the paper. And he held it up. He was a lawyer in international property rights. I don't know. So he put it down again. And he said, Mr. Dingwell, I hear you're interested in volcanoes. Why do you want to come to Munich? So I always put this up. And of course, when Munich airport was closed 10 years later due to Eyjafjallajökull, then that was quite a day in my life. So the aviation hazard is one of the fastest growing markets for our problem, because aviation, you probably all follow the story of how many planes are sold and how many airlines are growing, and the curves of the growth of this industry are spectacular. I don't know how the profits are, but the industry is spectacularly growing. And almost every airline has to cope with the fact that they could be potentially impacted by volcanic events. And so it's one of the easiest ways to explain to non-scientists and non-geoscientists why we do what we do. These are just the growth rates, projected growth rates from 2012 when it was put together, or 2011. And you see they're very large. There are very few industries growing at this rate. You know this as well. These are the I always say this is the 15 ways that a volcano can kill you, and this list is not complete, I'm sure. But you know that it's a spectacularly modern problem in the sense that everybody is interested in going laterally now. Everybody is interested in interdisciplinarity. You're always being put upon by the management of your university to be more interdisciplinary, transdisciplinary, to do things with more people. And most of the times it drives you crazy because you know what you want to do. You don't need to speak to others. But actually our problem contains all the potential you need for the rest of your life to be interdisciplinary, unquestionably. When they closed Munich airport, our phone did not stop ringing from phone calls inside the University of Munich, from the medical faculty, from the legal faculty, from the engineers, asking if they could work with us on volcanic ash. So people are ready for interdisciplinarity. But our inspiration is, of course, to understand how the volcano works. And I can recommend to you, no matter what you do, get your child or somebody else's child to try to draw a drawing of what you're trying to explain. And if you stare at the drawing long enough, somehow you will get some insight, I promise you. But over here, it's the way that I distort modern volcanology for my own purposes. I like to think that experiments are one of the three legs of a stable stool, which we sit on when we try to understand volcanology. Of course, you have all of classical, if I can use the word, volcanology, which I usually describe as the most elegant earth science that I know. The beauty of what physical volcanology is able to describe is breathtaking. You had to be very talented to be a good field-based physical volcanologist. And at some point in my life, I decided I did not have that talent, so I would do something else. In the meantime, of course, the whole world has become simulated. And you all know, and some of you probably do it, that simulations and theoretical and numerical expressions of theoretical approaches to processes are a backbone of anything, any human endeavor today, no matter what it is, from anthropology to zoology. That's all something I don't need to tell you. But the third one I feel I have to tell you, and that's why I'm here today, which is that in the solid earth sciences, volcanology has a very special place. It is very experimentally accessible. It is more experimentally accessible than almost any other field of solid earth sciences, and there are a lot of them. You can go all the way from clay mineralogy to rock physics and many in between. But in volcanology, the temperatures, the pressures, and the time scales are available to us in the laboratory, and especially the time scale. We don't need to extrapolate in time. We only need to extrapolate in length scale. And length scale, of course, can be something which is a big extrapolation, but it can be something which is a material length scale, which you can also capture in the laboratory. It depends upon what process you're trying to describe. So we're really in a sweet spot of accessibility of natural processes when we talk about experiments of volcanoes. And that's the attraction to me. It's always been the attraction to me. I realized that with what we already have in capabilities, we can do enormous inroads into how volcanoes work using volcanic materials. So you all know that this is the big business of volcanology. You all know that this is where all the money goes, 99% of it. This is okay, because volcanology is becoming data rich, finally. We're finally getting to the point where it's difficult to know all the data which is available, which is good, because eventually we will have something which is the equivalent of bioinformatics. We'll have geoinformatics, which will do the same thing for us. Yeah? And all of this, or the usefulness of all of this, rests upon an interpretation of the signals. So if I'm doing seismology, if I'm doing basic geophysics, I have a model in my head. Simple example, it may be a MOGI model for a point source of a seismic signal. So it's always on the working hypothesis of what has just caused what I have perceived. It can be simulated, but in order to simulate it, you also need fundamental property data of the system. You need to parameterize what is the magma capable of, what is the edifice capable of, what is the fluid system capable of doing, what are the boundaries of its behavior. Can I tame this wild beast in terms of reducing the number of possibilities for its behavior. And experiments inform that discussion because they give us constraints, limits on certain kinds of behavior, which we can then hopefully apply to our interpretation of this vast sea of observational data. Far from complete, it needs to be in the future, but growing very fast, this field of observations. One in Germany, just to remind me to thank Bavaria mostly, actually, but also Germany a little bit, and Europe, for funding 30 years of this work. Here you see a plot of processes. You see saturation, a nucleation, a growth of bubbles, a foam, and a fragmentation. So if you would talk to an engineer of various colors, if you would talk to a chemical engineer, or if you would talk to any kind of materials engineering, very easy to get them excited when you talk about volcanoes, because they have something for everyone. The complexity of these processes, the way they may interact with each other. Can you go up and down in this diagram? We think, yes, probably we can and do regularly. So far away from a simple linear approximation we have, but we strip it down into a linear approximation in order to isolate the individual parts of the system. Most important part of experimental work, ask the question in the right way so that the answer will mean something. The worst experiment is one where you get the answer, but because you so poorly designed the experiment, you don't know what the question actually is, which is being answered. So actually a good experimentalist is a good philosopher, and not just somebody good with his hands or her hands. Now, the basic premise upon which I'm going to discuss the rest of our results is this very simple diagram. This very simple diagram represents the relaxation behavior of liquid or molten rocks. On the right-hand side, you have glass, and on the left-hand side, you have a liquid. And the only difference between a liquid and a glass is time. In essence, if I choose the time correctly, I can have liquid behavior. If I choose it in a different manner, I can make a liquid behave like a solid. And this happens to magma all the time. And despite the fact that it is clear that we must be transitioning from liquid to glass in all volcanic eruptions, because we get the glass, it's everywhere after the volcanic eruption, and we know that the plumbing has been liquid, despite the fact that this transition from liquid to glass is omnipresent in its evidence. Nevertheless, the understanding of the relevance of this and the quantification of this took far too long to get its way into the geological literature. There were some hints in early textbooks. There's a beautiful book by Rittmann, and if you break it in the middle, about halfway, you'll find on page 300 and something or so, a beautiful little 10-line description of magma as viscoelastic material. And he says it so matter-of-factly that nobody bothered to pay attention to it. So this yellow line is the glass transition. It is the transition between a fluid system and a brittle system. It is the basis of the entire industry of glass making. It is where all glasses are made, up here, because as I use the example of a Coke bottle in a factory somewhere here in Mexico, making them every day, tens of thousands. How do they make them? They go to this yellow line so they can deform the glass melt. It has to behave like a liquid. But they don't go too far away into the liquid regime because they must preserve the shape as a glass. So they're playing this, riding on the edge of this transition, just fluid enough to be formed, but solid enough to be maintained. So we're crossing this transition all the time in eruptions. Sometimes the transition is crossed accompanied with crystallization, which is the example you see here, which is a lava flow on Etna. And if you look at this in focus, probably what you're all doing is looking at the incandescence and the little blocks that are falling off the toe of the lava flow. Clearly solid, clearly brittle, cracks, fractures, crusts, all this good stuff, right? But if you look at it again, defocusing your eyes, you see the whole tongue of material coming down. It's clearly not solid, it's clearly liquid. So this is a liquid nature and a solid nature, intimately touching each other in nature. Now we take a sample or an environment where we have a case of glass, very much glass in the system. This is a collapse of Unsen Dome. Try to turn down the volume if I can. I hope it's not too loud. This is one of the reproductions of television programs on the Unsen dome collapses of the early 1990s with the tragedy of loss of lives and so on and so forth. We're producing ash, we're producing glass particles here, but the dome itself is deforming all the time. And the dome, in my unconventional way, I will say to you, the dome is something like a rock glacier sitting on top of the mountain. It's slowly sagging down the sides of the mountain. It has crevasses all over the top of its surface. Yeah. Someday somebody will write a nice paper comparing the rheology of ice in ice domes and that of rhyolite domes. So, to quantify where that yellow line is, so we can say quantitatively what we can expect from a volcano, we go into the laboratory. The first thing we do is very simple and straightforward. All the technologies are simply borrowed from material science. We invented nothing. We simply put rocks in there. But actually just doing that led to great advances in our parameterization ability for magmas. So what you see here are two devices that you will see. I'm sure you have one on your campus somewhere in material sciences. On the left you have a high temperature viscometer, the kind of thing that you learn to measure viscosity in, maybe in high school with some motor oil. On the right-hand side, you have a dilatometer, something which ceramics uses all the time to measure expansivity, to measure deformation of all different kinds, creep experiments, and so on. And using these two devices, you see that we're measuring the same property, but we're measuring it in very different ways. We have to do that because the viscosity varies so much in its magnitude. There is no one device that can give us all the information. So we get the information. Here are viscosity curves. This is the logarithm of viscosity. So you see it's an enormous range of viscosity, 15 orders of magnitude of the ability to flow. 15 orders of magnitude of stress at a given flow rate. Please appreciate how big that is. Versus reciprocal temperature. You have the high temperature data, the low temperature data. And if you are unimaginative like some laboratory people like me, you do this for decades. And eventually you build up something big enough that you can actually do multi-component predictions. This is total alkalis versus silica. This is the range, one of the projections of the range of the chemistry of the Earth's liquids, and each one of those data points has a curve over here. So now I'm going to take you on two trips, one slow and one fast, field trips if you want to call them, through the glass transition. They're very different field trips, you'll see. We do the fast one first, okay? We're going to go from the liquid to the solid. Here's how we do it. We used to call it our fragmentation bomb. We don't call it that anymore. We don't call anything a bomb anymore. So now we call it our experimental volcano. That sounds cuter somehow to the security authorities. So what we have is a big tank which does nothing. It just sits there and catches whatever comes out of the experiment. It looks optically like the most important thing in the system. Maybe it is, but it doesn't have to do anything except stay there, not chemically interact with the samples, not fragment the samples, just catch what comes out. It's the atmosphere. It's our sample of the atmosphere, okay? In the future, we hope to do a lot of chemistry in there. There's a lot of atmospheric chemistry done in big tanks like that, aerosols and so on, and we think that if we can get enough input from them, you'll see a lot more about the chemistry of what happens here. But what we do is the magma. The magma we put into a high pressure, high temperature system. Again, moderate pressures, moderate temperatures, much less than what we need to do much of experimental petrology, which we've been doing for 50 years. And therefore we have a magma chamber, and above the magma chamber we have the atmosphere. Of course we have to keep them separated for a while, and then we remove the separation. So we have a high pressure in the magma chamber, we have a low pressure in the tank. And we literally fail the barrier between them, and so the sample in the magma chamber suddenly sees the atmosphere, decompresses, and now it has to do something. It has to decide what it's going to do. And it does in nature all the time, of course. We have eruptions, we have failed eruptions, and so on. And what it often does is it erupts explosively. And we were the first people who were able to actually produce ash by fragmentation of magma simply by decompressing the sample. It could not be more simple. The great constant of volcanism is decompression. There's No way around it. You can argue thermal paths all day long. You can say constant, you can say adiabatic, you can say up and down due to latent heats, but decompression is unavoidable. It is the great constant of volcanology. Things come to the surface. And as they do, they decompress, and if you do the decompression fast enough, even though you're dealing with a highly viscous liquid, it's sitting there in a container, it does not have any rigidity, it has to be held in position by an external container. Yet if I attempt to decompress it on a much faster time scale, it does not respond viscously like a liquid. Suddenly it discovers its rigidity because you're asking for deformation beyond its relaxation time as a liquid. It cannot behave as a liquid, it behaves as a solid, it fails. And it fails macroscopically, and it fails thoroughly in a bulk way, such that the entire cylinder of rock initially here, you'll see one in a moment, ends up being a cloud of ash above. And we know that we have eruptions of thousands of cubic kilometers of ash from single sources. So this is the spectacular through-going nature of the crisis of materials that these volcanoes generate. It's truly remarkable. It's not necessarily happening in the same way on other planets. We now know there's about 5,000 other planets already, right? We know that 20 or 30% of them are terrestrial planets or something. I was recently at a lecture where they described to us how many systems we now know of. Wouldn't it be wonderful if we could know more detail? Comparative objects. Mars and Venus, probably very different in terms of the fate of the volcanic systems when they arrive at the surface. So this is a schematic of the diagram. I know that these things are not pretty to people who don't do experiments. I apologize. Basically, it's very simple, as all good experiments are. You have a bubbly magma. It has to be bubbly. We need those bubbles. And you have the atmosphere above. Before, they are separated by a pressure membrane. Afterwards, the decompression wave marches into the sample, and as a result, this sample begins to explode. Why does it explode? Because the sample is decompressed macroscopically, but the bubbles inside don't know it yet. The rigidity is allowing them to maintain their pressure, and their pressure differential to the outside is higher than the strength of the rock. It's as simple as that. Okay, I'm going to show you three characteristics of these transitions: the threshold, the speed, and the permeability. This is a video showing you exactly what happens when we do one of these experiments. If I can get my mouse in the right place. So what you see here is a dome rock with beautiful big phenocrysts going up simply as a result of decompression. So there's no doubt that we can destroy these things with decompression. You're watching a video of it happening. Yes, this is happening at room temperature. We see exactly the same thing happening and the same products produced at 1,000 degrees Celsius at magmatic temperatures. This is another video of a pumice going up. Now it's laid on its side to show you the detail with which we can observe these things. One of these two videos works. I never remember which one it is. It's the upper one. Here we go. No, not going to work today. Okay. There we go. This one doesn't. See the ash? That's new ash. We clean these samples very carefully. That's new ash. That's not dust. Now look at the detail of what's happening inside your volcanic dome. It's going to be a while before we parameterize all this, right? It's a fascinating complexity which is possible in these systems. And this is with no gradients in material properties. On top of everything else, if you go over a few hundred meters in a dome, you change the state of the system. More crystals, lower temperature, and so on. So it's a whole playing field which we can observe with high-speed videos and get information on. So while that's happening, of course, in the dome, in the tank above, it's hard to think and do this at the same time. In the tank above, we're getting the results. And the results look like this. So here comes the gas. It's all under gas pressure, as are volcanoes. And here comes pyroclastic column. That is freshly produced volcanic ash. Lots of it on a relative scale. And you see that it runs on and on and on like a steady state for what is actually only a few milliseconds, but it's long enough that you can do physics here. You can do all the dynamics. You can do the speeds, the accelerations, the grain sizes, the trajectories, you can do a lot of video analysis on these materials. You also show interesting interference phenomena, which probably have to do with the details of our experimental tank. So we can do the studies of the ballistic phase of the initial phase of these volcanic blasts in the laboratory today. So, what do we need to do it? This is it. We need pressure. We need a pressure differential. And the pressure differential that we need can be parameterized with one property of the system, porosity. And these are all natural samples. So you see that nature gives us a few percent of porosity all the way up to spectacularly over 80% of porosity in natural magmatic cooled samples, okay? And we put them back under pressure and then see what it takes to explode them. So what we see here is a kind of a dynamic tensile strength which varies from about 30 to about 3 megapascals depending upon the bubble content. So if you have a system with variable bubble content, which you often do, generally do in magmatic systems, you know that this material is going to fail earlier and much more efficiently than this material. And that's the reason that the biggest eruptions are dominated by bubble-rich materials. They're the weakest materials and they go first. Okay? This is not the same as saying that we have a topological boundary for fragmentation. The older ideas were you close pack bubbles which are spherical, you get to 70-something%, and it must disintegrate because it's a mathematical topological consequence of that bubble fraction. It's not true. It's not how it works. We get reticulates on Hawaii that go almost up to 90% bubbles. You can get polygonal foams. These things can happen. The reason they don't happen is that the strength of these materials is overridden before they get to those vesicularities. But anything can be fragmented and any vesicularity can occur in a pyroclastic material and does. We know, we see it. How fast? Slow. Counterintuitive for a lot of people first time they see it. The speeds of this fragmentation front are very slow. We can get them down to about 10 meters per second. The acoustic velocities of these rocks in the brittle state are kilometers per second, the same as every other rock. +1, -1, depending where you are. But the process of disintegrating these materials, eroding, whatever you would like to call it, to get an intuition for it, is taking place at a very relaxed rate of descent into the column, okay, into the magmatic column. In fact, these rates of disintegration are so slow that they're in the range of ascent rates of magma, which I think is one of the most important observations so far in the talk, because it implies that you can feed magma at the same speed that you produce ash. And that implies that you have a matching of rates that can allow an eruption on and on. You have a system, a chemical engineering system in steady state, which is feeding this volcano over days or weeks or whatever you like. You don't necessarily need sharp discontinuities in what's going on. You might have some systems that are just milled away at the same speed that you're able to feed vesiculated material to the front. A speculation on my part. If you mismatch these speeds, you get other kinds of volcanic phenomena, and you must. So if you have a fairly static magmatic system which simply explodes from the surface or near surface, something like a Vulcanian explosion, then you obviously have some erosion. So that's a case where you have the speed of erosion of the system overrunning any kind of supply because there's no supply happening. It's a static system on the top of the dome. Yeah? And you can imagine the opposite. You can imagine that the ascent rate is faster than the fragmentation or somehow more efficient than the fragmentation. What happens then? We see in nature systems which throw out ash blankets for a long time, and what happens when the dust clears? You see a dome rising. No fragmentation anymore. The fragmentation front has risen to the surface of the Earth. There's no more pressure differential left, and it just dies in that state. So I think we can understand the rationale for different styles of explosive eruptions and their time dependence by understanding how the dynamics of the explosive process versus the dynamics of supply varies. Gas loss. All volcanoes degassing all the time, 100% of the time. They're great degassing centers. Although we don't know enough about diffusive degassing, we can certainly say volcanoes are great degassing centers. And it's the gas pressure which gives us the energy, the potential energy, the pressure volume, potential energy, which explodes these materials, which blows them through the tensile strength. So can gas loss be with this fragmentation? Probably. You have to go into the right range of rates, and you can have a competition between the two alternatives that any volcano has, to let the gas out by itself, or to have a problem with that, and to have the gas take the mountain with it when it goes. You see? We can look at these explosive eruptions as, to be provocative, as industrial accidents in volcanic degassing plants. Okay? And we try to quantify what that is. We measured the permeability of all the samples that we fragmented in our machine. It was a whole PhD thesis, poor guy. Great work. And he showed that at low permeability, all the parameters that we have to describe, one of which is the energy density, they don't move. It doesn't matter what the value of permeability is as long as it's low. Gas loss is not playing a role. But if you let the permeability creep up as you come towards me in this diagram, eventually what are normally constants in our experiment become variables. And what that means is the gas is outrunning the fragmentation. Okay? It's running ahead of the fragmentation of the system. It's obviating the need for fragmentation. And so you have the case of a potentially explosive volcano simply blowing its gas off in between the explosions. So let's take you on the second trip. We'll try to get through on time here. Let's go slowly through all of this. What you saw looked slow, but it was all high-speed videos, and it was all millisecond experiments. So here we go, slowly through. Does nature do it as well? Sure. Nature is famous for slowly erupting volcanoes, dome extrusion events. All right, so here, not a in quantitative, converted in that. But you do get extrusion of volcanic rock. And then you get these incidental failures and flank collapses and so on over steepened domes. So if we're trying to slowly through the glass transition and to understand how it influences the system, we can measure a lot more. The great advantage of slowing things down is your sensorics, which you can apply to the experiment, goes up. So you can measure many more things. And so we know that at least three things must be happening. Congratulations to us. It's going to be complicated, right? So we know that there's viscous heating. We can quantify it. It's fairly straightforward. The equations are fairly straightforward. They scale to the strain rate squared. We know that there are great suspension effects in these liquids, so understanding their rheology also requires understanding their crystal content, their bubble content, the chemical effects of producing the crystals and bubbles, which is differentiation in a magmatic sense, and the physical effects of the presence of the crystals and bubbles, which is the physical rheology of the system. And once you got that figured out, once you got that calibrated, you have a third effect. You have this structural effect of the liquids. If we push these liquids into the yellow zone, they start to behave no longer as liquids. They start to lose their liquid character. They start to behave with rigidity. And rigidity is a problem because it's an elasticity. It means you're storing the energy somewhere. You're not dissipating it. Well, if you're storing the energy somewhere and you keep pushing, sooner or later you're going to have a problem because that energy is all still in the system somewhere. And that's basically what leads to the explosion. So here you see what happens to the viscosity as a function of strain rate. As I push into the yellow zone, I fall off the edge. I fall off the cliff of Newtonian viscosity, and I have what we call shear thinning, well described in the polymer literature, well described in many literatures of rheology. And basically, these materials are sheared out of equilibrium. They're sheared out of existence. You can literally mechanically push the liquid out of thermodynamic equilibrium using a big press. Okay? And this, of course, happens about the same time that this happens, which makes things very complicated. So here is an example of how we measure the viscous heating. Again, depending on who you would ask, they would come up with all kinds of fantastic ideas of how to measure viscous heating. If you ask an experimentalist, they say, we'll measure it, right? So we stick thermocouples into the samples. Here is before the deformation. Here is after the deformation. You see the bulging of an unsupported uniaxial compression of the cylinder. And we measure the temperature increases. Here we do it with actual rocks, beautiful dome lavas. You see we have to use pretty big samples in order to get anything like a characteristic heterogeneity of the sample in the experiment. It's tricky. Here, the scaling is the distance between crystals, the size of the crystals. That's the critical scaling in this material scaling. So we don't have to worry about kilometer-size scaling for using these results. A lot of people know that scaling is important, but a lot of people misunderstand what scaling is relevant to a particular experiment. This is not fluid dynamics. So here you see the temperature beginning to run away. We can beautifully see the temperature increase. Look at the tiny changes in temperature we can record. 1/2, 1 degree Celsius, and it begins to run away. And we have a check on whether or not these temperature runaways are right. We can look at the rheology which we're observing at the time. And because the rheology depends on the temperature, we can actually indirectly calculate whether the temperature rise is consistent with the drop in viscosity that we see. And they match beautifully. So not easy to do at 500 degrees Celsius where you have an interactive temperature control in your device, but you can actually determine the onset. We believe now that this viscous heating may be a reason for the longevity of certain rhyolitic lava flows which should have died much earlier, but somehow still keep going. We think they're heating themselves as they go down the slopes. This is the attempt at a parameterization. I'm not going to say anything in detail except look at the yellow line, look at the blue line. You see that they cross. They cross at an interesting temperature, actually, for volcanic products. It's still pretty hot. And the crossing of these two lines is dividing a regime where you will heat them first as you increase, as you accelerate the deformation, heat them up, which will make you avoid explosions, because as you heat them up, the viscosity goes down, and you drift back away from the glass transition, from this ugly fate awaiting you. Or you're on the other side of the crossover, where they will fail before they start to heat, because they scale differently in strain rate. It's a beautiful interplay of two fates, two possible fates of volcanic systems. They make earthquakes, as you all know, I'm sure. The most earthquake-rich places on Earth are volcanoes in eruption, and hundreds and up to thousands of events, depending on how small you can measure an earthquake, how sensitively. They're tiny. They have not historically been the great inspiration of seismology, no question, but there have always been a few crazy people who were more interested in volcano seismology than anything else, including some of the fathers of seismology in Italy, of course. And here we have acoustic sensors on these experiments. And acoustic sensors we can parameterize in terms of the number of events, when they occur, and what energies are associated with them. And what you see here is something that looks, I hope, to you like a catastrophe about to occur, and it is indeed. It's the climb up in acoustic events, which are minor cracking in the sample before it catastrophically fails. We get the ash. So we can begin a science of ash which is experimentally pinned down and calibrated now for the first time in history. It's great to measure volcanic ash. We desperately need to understand the complexity of volcanic ash and its interactions with the environment. I'll probably spend more time working on that than anything else in the next 5 years. We'll come to a diagram showing how potentially complicated it is in a few slides. But in order to understand all of that, we now need to understand the fundamental variables that control the initial state of volcanic ash. Where are we coming from? What does it depend on? What do I have to deal with? And here, for example, we can determine, we get the ash in the tank, we collect the ash, and then we do everything you can possibly imagine doing to ash, doing the particulate material, sedimentology of ash in the laboratory. Grain size analysis, specific surface analysis, microanalysis of the chemistry of the surface of these particles, and so on and so forth. This is just one example showing porosity of samples versus the weight fraction of particles in the ash fraction. And you can say as you increase the pressure, you get more ash, you get more fine particles. It's because you have more energy available to produce a greater surface. It costs energy, specific energy for surface fracture. Everything makes, in a qualitative sense, everything makes physical sense. Grain size distributions in units of diameter, phi units, sedimentology, if you will, or classical physical volcanology. You see that these maxima shift as we shift the experimental parameters, in this case, pressure. Okay, I'm through the 2 trips that I wanted to take you on. The last thing I want to do is just give you a flyby at 10,000 feet of what I think are 5 very exciting frontiers of this work. These are things that I hope to be able to make a couple useful contributions to before I have to stop doing this, but these are things that I think will get a lot of attention in the next generation, which is beginning to understand volcanic processes, because these people are young and fairly open in their minds and unfettered by prejudice, and these are very promising areas of research. Let me show you this one. We talked about viscous heating. Viscous heating actually has consequences. If you do enough of it, it actually changes the state of your system. And this is a frictional rig experiment on volcanic dome rock. Both sides of what you're about to see spinning are dome rock, a dacitic dome rock. And what happens if you have a fault which runs straight through a dacitic dome? The rock is already at 600 degrees Celsius, and you start pumping more heat into it. Well, you start to remelt the rock. And you may know that we now propose from Mount St. Helens that there's clear evidence of pseudo-tacholites, of frictionally melted rock inside of volcanic domes. It's weird. I mean, when I was a student and I talked to my structural geologists, who were very great guys at Newfoundland at that time, world-class people, and you would say you were interested in magma, then they would do this. You know, they would say, oh yeah, magma, the great destroyer of structure, right? The black spots on the structural map of the Appalachians. I remember them very well. But there's a lot of kinematics in magma. There's a lot of kinematics in magma. It may not be a schist where you can determine 5 deformation phases, okay. But you can determine a lot about the deformation during the events which led to the eruption. Second example, we now believe that these materials are failing at depth and are rehealing. We believe that the fragmentation of these things is a whole lifetime that they have moving up the conduit until they eventually get out at the top. So we believe we make ash subterraneanly, okay? So subterraneously. And this is an example of the question, and you'll see 2 cylinders. The white is the sample, by the way. The black in the middle is just a crack in the back of the furnace. Don't worry about that. The 2 big white cylinders or orange cylinders, whoops, are the 2 parts of rhyolite which are now being cycled together, being closed and open, closed and open. And we think that this happens, we think it's the origin of flow banding in rhyolites. Since about 10 years now, it's published in Nature and Geology by 2 different groups. And what we're measuring is the stress that is required. This is Jan Lavallee's work. We're measuring the stress that's required to pull them apart. And you get a fundamental relaxation time before it's completely sealed together, before you get something like a tuffosite, where you know it's broken from looking at a tuffosite, but if you crack it, you'll get a conchoidal fracture which runs clean across it. No heterogeneity of properties. Next frontier, ash. If somebody asked me what could I do now, which I can be sure of being employed in geoscience or doing for the next 30 years, I would say ash in the environment. Ash in soil, ash in crops, ash in our lungs, ash in the air, ash in the oceans, ash causing algal blooms in the oceans, and all kinds of stuff. This is an attempt by Iris and Delmel to explain what ash is capable of. And it's not complete. Nothing in geoscience is ever complete. So this is a huge field, and it allows us to put ourselves in a unique position if we can make ash in a systematic way in a laboratory, because then we can conduct laboratory experiments on chemical reactivity and so on, where we can reproduce. And we know every time we take a shovel full of ash, we know exactly where it came from because we made it ourselves from rocks. Okay. We're doing experiments with something we call a reactor, ash gas reactor. Actually, it's Ana Casas who's doing these experiments. She's a good chemist, and she's doing the interaction of powder mixtures, which must be exposed in a reproducible way, their surface, to a reacting gas. So the way you do this is you rotate them in a tumbler. So nothing is being reactively stuck and glued to each other. There's no loss of permeability of that powder sample. It remains in its initial particulate form, the simple mechanical trick of tumbling it. There's no fragmentation in the tumbling, or at least we hope. We do up to 300, 400, 500 degrees Celsius, these exchange experiments, where we study what the ash does, or what the gas does in terms of depositing components of the gas back onto the ash surface. And we came up with this idea of volcanic sequestration, the idea that you could actually park sulfur in ash deposits and take it out of the atmospheric system, just to be provocative. And we think that you can park up to a half of the sulfur, which is co-erupted with ash, back onto the ash surface and have it fall out with the ash and not be a long-term challenge or a midterm in the atmosphere. There are lots of experts on volcanic ash dispersal. You know, back in 1986 or whenever it was when Chernobyl erupted, suddenly everybody wanted to know about dispersal because it was about this nuclear fallout cloud coming over Europe, right? Codes began then, simulation codes, and since then volcanologists have kind of taken over, and there are many world-class results on ash dispersal. But ash dispersal also means we need to understand the state of the materials as precisely as we can. The simplest parameter that goes into ash dispersal from the material point of view is the grain size. But what if we don't understand the grain size entirely? And we now know in the meantime that it's complicated. We now know in the meantime that the grain size can change in the air because we can have what we call aggregation. This is a video I need to play a couple times because you won't be looking in the right place. But if you look at those circles, you'll see ash falling from the eye of Fiatlet cloud onto the finger of Corrado Cimarelli, which is pretty soft stuff. And you see what happens when the ash lands. I'll do it one more time. 1, could you see it? 2. Disintegrates into 100 or 1,000 particles. These are ash aggregates. These are large clumps of ash which are coming down with a grain size which represents 1,000 times their individual ash particle diameters. And they disappear when they land. Good luck. You go out there later with the shovel and you measure the grain size distribution, which involves a certain amount of agitation and manipulation of the materials, and then you try to estimate constraints on your dispersal codes based on the grain size of the individual fragments. What happened to the aggregation? You don't even see it in the geological record. Now, you do see aggregation in the geological record in other environments. We see lots of pellets in the pili and so on, but obviously not everywhere. So we do experiments. What else do we do? Anybody else would go out and measure it in the field, but we say, how can we do it in the laboratory? So we make ash aggregate particles now in the laboratory. We do it with the help of a company which is normally worrying about putting your breakfast cereal into the form of aggregates. Aggregation is a huge thing in the food science. Food science is huge anyway, you probably know. You probably get emails from your vice president telling you to work with food scientists. I don't know, we do. They do everything, food scientists. And one of the things they do is aggregation. They spray amorphous sugar on your cereal and so on and so forth. Well, here we're spraying HCl and sulfuric acid onto ash in what is otherwise being used for breakfast cereal. They let us do it. We promised them we would clean it up very carefully afterwards. And so with this, we're able to produce aggregation. And we can produce, one of those is experimental and one of those is real. We can produce aggregation of ash particles beautifully in a laboratory. And we're inferring what it takes to aggregate ash. And there are many possibilities. There are electrostatic considerations. There are also chemical considerations of drying to salts from the acids, which then glue the ash particles together. And our good old friend aviation. And I was contacted by a Chinese postdoc for the first time in my life. I said, come on over. And it's a gentleman named Wen Jiasong, and he received €1 million, believe it or not, from the Volkswagen Foundation to study the problem of ash ingestion into turbines. And everybody's interested in this now. Chinese are very interested in it. They don't make their own turbines yet in China. They buy them. They don't like that, of course. Eventually they'll make their own, and when they do, they want them to have the best resistance to ash and anything else. Of course, they're just as interested in the military as they are anything else. So obviously, we have a complicated technology when we talk about turbines, but we also have complicated material going in. And although everybody was worried about the complicated technology and worried about how we can monitor it with LIDAR and so on, nobody was worried about whether or not the actual identity of the ash makes a difference. So, then comes the petrologist, then comes the geologist and said, there are different kinds of ash. Maybe it makes a difference. Some of them are 100% crystalline. Some of them are 100% glassy. Some of them have softening temperatures at 400 degrees. Some of them have them at 800 degrees. So we started to work out a parameterization of the thermal fate of ash when you reheat ash particles. And what you see here is time series analyses of optical dilatometry in a high temperature furnace of how ash refuses or softens actually only at the glass transition and wets the surface of jet turbines. And we're deeply into this now. I just wanted to give you a taste of the fact that we're working on it. because time is slowly now coming to an end. Last thing I want to show you was the serendipitous result. It was the thing that nobody saw coming, that we did not see when it happened for years until we got the right videos. And when we saw it, we thought that the video camera was malfunctioning because we had whiteouts of frames in the video. And we sped up the speed of the video camera. Miguel Alatorre was involved in this work in the very beginning. And when we sped up the speed of resolution, time resolution of the video, we saw the following. And this is you'll recognize right away for an experiment this is. Here comes the gas. And here comes the ash. What a beautiful constancy and pulp. And here comes the lightning. And we didn't put any electrical fields in this experiment. The process generated the electric field gradients to produce the lightning. This is the most natural lightning experiment ever done. I can say that because we walked across the street, as always happens in Munich. You do something new, and then you find out there's an institute that does it across the street at the technical university, and you go, oh, God. And you go over there, and you say, look at this. And it's very often that they just smile and send you away. But this time they said, wow, you know what we have to do to produce lightning in our Lightning Institute? You know, we had to produce 40,000 volts, and we're experts at doing it, but it's not easy. And you guys just get it for free, you know. So we generated a lot of excitement. I remember Corrado Cimarelli, who's leading this project now, he said, it's amazing. I walk in open doors wherever I go. They can't believe that something so natural and so similar to near-vent lightning that we see in nature is so easily produced. And this last example is the example that best describes what you can use all this stuff for, which is you can monitor volcanoes using electric fields. You all probably knew that, but you can probably produce a proportionality between the volume or the mass of fine ash and the total electric field discharge occurring at the volcanic vent. So you might have a real-time way of saying exactly what the flux of fine ash coming out of any volcano in the world is if you have the antennae set up around the volcano. And this is being tested now at Sakurajima, and we might have a way to know what the flux of ash is in Eyjafjallajökull when it erupts the next time in the middle of the night, in the middle of December in Iceland. No? Otherwise not easy to do. And you know, for ash dispersal models, the most embarrassing fact is that the source function is the most difficult thing to get right. We know that infusion rates and explosive rates of flux can change by a factor of 2, just like that, because something happened in the subterranean plumbing system, presumably. So just being able to monitor it is probably going to be the answer in understanding these systems better. It's a result we didn't expect to see. The only reason we saw it is because we were there, and I'm sure you've heard from other experimental scientists that that's the best argument that there is for experimental infrastructure in any field, anywhere in the world. If you want to explain it to governments, just say, look, things are going to happen. If you don't have any competence or any expertise, if you don't have a cadre of people who are able to observe, then you will not be the people who discover it, you will not be the people who can describe it first, and you will not be the people who can develop any potential applications or technology first, because you'll be in the back of the line. So that's the most important argument you can make to science policy and science politicians, is that just having infrastructure in vital areas does not mean you're going to get the routine data that the infrastructure promises. It also means that you're going to get the unexpected data that the infrastructure puts you in a position to happily and luckily receive. Thank you very much.